Okay, so for those of you that don't know who I am, my name's Sam LADAK. I'm based at Cardiff University in the UK. I'd like to thank the organisers for the invitation to give the talk. So today I'll be telling you about our latest work in Cardiff, whereby we fabricated sub 100 nanometer 3D magnetic nanowires using two-photon lithography. So I'd just like to acknowledge the team, obviously a collective effort with respect to work. So Wolfgang Langbein has done much of the optical instrumentation. I'll be talking about Jaworski, fabrication, and then Matthew Hunt, MFM, Arjen van der Berg, the micromagnetic modeling. And then towards the end, I'll be telling you about how we've actually moved some of our measurements to the synchrotron, for which Peter Fischer was also instrumental. Don't look down, it seems. So this is an overview of the talk. So I'd like to start by kind of building upon Amalio's introduction, a very nice introduction. So I'll provide a motivation for why it's interesting to study 3D nanostructured materials from a Cardiff point of view. I'll talk a bit about our most recent work. So in Cardiff, we're mainly interested in 3D artificial spin-ice systems. I'm going to give a very brief introduction to those systems and some latest work whereby we've observed magnetic charge crystallites in those systems. I'll then talk a bit about how that actually motivates us to actually take a commercial two-photon lithography system. This is really not working too well. Improve the instrumentation such that you can actually realize sub 100 nanometer feature size. I'll then show how we can actually fabricate a proof of principle system and observe domain wall pinning in those systems. Good, okay. So beautiful introduction from Amalio. So why is it interesting from our point of view to study 3D nanostructured magnetic materials? Well, as we all know, we can take seemingly very simple three-dimensional primitives, so just a cylinder, and you can immediately realize spin textures that you would normally not see in planar systems. So, and one example is just obviously the block point domain wall, which most of you will be familiar with. You can then actually take that 3D primitive and use it as a building block, and you can carry out some sort of transformation. So you can either bend it or twist it. So this yields curvature and torsion and additional energy terms in the form of effective DMI and effective anisotropy interactions. And Dennis Makarov and Dennis Shika will be talking more about that later on. But we're more interested in doing something quite different. So we actually take these kind of 3D building blocks that I just talked about, so 3D magnetic nanowires, and we arrange them into three-dimensional lattices. And we do this in order to study the collective behavior. So we're interested in the frustration, the ground state ordering, I'll be talking about that more in a minute. You can also do a combination of those two things. So you can take some sort of building block which has got some curvature, and you can place that into a three-dimensional lattice, and that yields kind of gyroid structures similar to what Amalio has been talking about earlier. Okay. Right, so I'm going to give you a very brief introduction to 3D artificial spin-ice, just mainly because Laura is going to give a nice in-depth tutorial on Thursday. And so the spin-ice materials are model systems for studying frustration. We have this, this is not working too well. We have this pyrochlore crystal geometry, rare earth spin sat on corner-sharing tetrahedra. And so the minimum energy configuration on an individual tetrahedron, something known as the ice rule, which is where two spins point into the center of a tetrahedron and two spins point out. And there's 6 possible ways to realize the ice rule, and that yields 6-fold degeneracy. And that degeneracy really stems from the three-dimensional nature of spin-ice. So then you can take that kind of pyrochlore crystal geometry. You can take an individual tetrahedron, you can sum over the many tetrahedra within a spin-ice crystal, and then you can study the ordering, and then you find lots of exotic physics, a lack of ordering at low temperature, so some residual Pauling entropy at low temperature. And you can also study defects that behave as magnetic monopoles also. But in order to study this type of behavior, because this is a bulk solid state system, you actually need to use bulk techniques. So you need to use things like heat capacity and magnetometry. So it'd be rather nice if you could actually find some sort of artificial analog where you can actually directly observe the spin dynamics. And that is basically the idea behind artificial spin ice. So a single domain magnetic nanoisland is a very good approximation to classical icing spin. And so what you can do is you can arrange single domain magnetic nanowires into simple 2D geometries in order to capture some of the basics physics of spin ice. And this is really a really nice field now. Lots of nice physics has been done with these nanomagnetic arrays. I don't have time to talk about it, but there's a nice review at the bottom there by many authors, including Chris and Laura. But from the point of view of trying to emulate kind of basic spin ice physics, there is an immediate problem, and that stems from the fact that you've moved to 2 dimensions. So we no longer have a situation where every spin is making the same angle with each of its nearest neighbours. We have a situation instead where we've got two interactions, so a nearest neighbour interaction and a next nearest neighbour interaction. This breaks the degeneracy of the ice rule. And so if you're naive and you're relatively young, you might think to draw a picture, something like this, and this is what I drew back in 2010. I thought it would be great if you could actually make some sort of 3D artificial spin ice whereby you actually capture the same geometry of the spins in bulk spin ice. We're kind of making progress towards that. Okay, and I won't talk about this in detail, but yeah, there's lots of people that have had similar ideas. So you can look at layered structures, nice buckyball structures, building blocks of diamond bond lattices, and these nice chiral 3DSI systems also, as I said. So Laura's got a tutorial on Thursday, so I won't dwell on this. But in Cardiff, what we do is we use 2-photon lithography, which Amalia has given a nice description of. So what we do is we use 2-photon lithography to define a diamond bond lattice within a negative tone photoresist. And so having done that and done the development, we actually just use physical vapor deposition to actually coat the surfaces of the polymer template with permalloy. And so what you end up with then is basically a unit cell of 3DSI where you can define a number of different sublattices, so L1 to L4. And this is what a typical structure looks like under the SEM. So as Amalia said, one of the nice things with TPL is you can go over very large areas. This is just 50 by 50 microns laterally. We could go bigger, 10 microns in height. If you look at the surface here, you can see in principle you've got access to each of those 4 sublattices I talked about, which potentially means you might think that you could use some sort of scanning probe microscopy in order to actually image these systems. So with respect to the nanowire dimensions, so we have a width of around 200 nanometers. So that's probably the best you can do with a commercial 2-photon lithography system as written. And then a length around 860 nanometers. You can do the micromagnetics and you see that these systems are a single domain. Okay, so you've made these systems, how are we going to measure them? That's another challenge. You can do AFM and you can see that you can actually accurately reproduce the surface topography. If you're careful and you use the right MFM tip, you can actually do MFM, and you can see that we've got nice single domain wires in the middle panel there, and then you can do a set of experiments whereby you apply a number of different field protocols and you find that you can recreate all of the vertex states that you'd expect to see in a conventional 3D ASI. Okay, and so once you've got this system, what are you going to do with it? Well, we're interested in ground state ordering. So these are 3D ASIs with only dipole energetics, and so the phase diagram looks a bit different to conventional spin ice. You can do the Monte Carlo simulations as we've done in this 2023 communication physics paper, and what we expect to see as the ground state is this kind of what we call a plus or minus 4Q monopole crystal. It's where you tile all in and all out spins. And so that's what we're expecting to see as the ground state. We do what you do in traditional kind of 2D ASI. We take our system, we subject it to a 2D demagnetizing protocol, and we see what we see. And we certainly don't see large sections of ground state. What we see is a mashup of 3 different states. We see only small regions of what we call this plus or minus 4Q charged crystal. We see patches of single charge crystallite, and all of this is superimposed upon this kind of type 2 ice background. Okay, so there's quite a few reasons for why we don't actually realize the ground state, we think, and this can include broken symmetry of the surface, but also the fact that we're using this deterministic in-plane demagnetizing protocol, which very much favors these kind of type 2 vertices which have this in-plane moment. And so really, if we want to try to achieve the ground state, what we need to do is we need to actually move to a thermal 3D ASI system where we need to shrink the wires such that your magnetization is firmly unstable, and essentially your anisotropy becomes comparable to KBT. And so your system can firmly explore its energy landscape. Yeah, and I guess it's been pointed out already that with a commercial kind of TPL system, the best you can get is maybe 180, 200 nanometers as written. To actually realize the thermal 3D ASI, you can just do very simple Nanomagnetism calculations. You need to be well below 100 nanometers, probably around 70 nanometers, a few nanometers of permalloy in order to reach that regime. There are tricks you can play, so you can do pyrolysis, which is a thermal degradation. So you take your resist, you put it in an oven, if you like, at some temperature, it reduces uniformly. But we've tried this. We find problems in maintaining the 3D geometry. There's another thing you can do. You can just take your template, you can subject it to an oxygen plasma, but for the times that we're talking about here, you really increase the roughness of the resist, and then your wires are no longer single domain or icing-like. And so instead what we opted to do is to take a commercial TPL system and try to modify it. So your TPL voxel size, so voxel is just a 3D pixel, it just scales with the wavelength, so you might naively think I can take a wavelength of half of what we normally use, and hopefully we'll be able to reach the right kind of feature size. And so a commercial system works in the infrareds, so 780 nanometers, that normally gives you 200 nanometers, so we'd want to roughly half this. Sounds very simple, but in fact, if you think about it, if you just half 780, where does that put you? That puts you right in the UV, and all of the standard resists that you would buy will then have photoinitiator molecules that are tuned to the UV, and therefore you won't get 2-photon absorption. So you're just going to end up with lack of 3D selectivity. But if you scour the literature, you can find a combination that works, which is lambda equals 4 or 5 nanometers with a special acrylate-based solution with no photoinitiator, actually. And so what we did is we took this approach. So we took the commercial nanoscribe system, we modified the optics and electronics such that any student can still go in and just use the standard software, and they can write a normal structure. It will just be reduced by roughly a factor of 2. Okay, so having done the instrumentation, we wanted a proof of principle system. We don't normally study domain rules, but we thought it'd be quite fun to make kind of sinusoids of varying periods along the length. We're going to vary our sinusoid length, fix the amplitude, and we're varying the length between 1 to 5 microns, with the length defined on the picture on the right there. And what we're going to do is we're going to do all of this very close to the polymerization threshold, such that we can induce a bit of roughness in our 3-dimensional nanowire, and so we can pin domain rules. Okay? Good. Okay. So our procedure then looks very similar, at least from the point of view of the student, it looks very similar, right? So we take our resist, we place it on our substrate, we use a different laser, we expose, and then we use line of sight deposition. And we can do that to realize any 3-dimensional structure just on a much smaller length scale. Okay, so this was the exciting result. I was very pleased when we saw this. So what we've done here is we've varied the effective exposure, and this is the mean length of the wire. And you can see that we're now getting down to 68 nanometers. So this is comparable to what you'd get with VEBID in many respects. And you can actually see that, yeah, you've got control over the, as you might expect, of the feature size with the effective exposure. Okay, so those 68 nanometer wires actually proved to be fairly unstable. And so for the investigation that I'm going to be talking about, we're going to look at wires just a little bit bigger, so 80 nanometers in width. So these ones were capable of withstanding our crude scanning probe microscopy procedures. And you can see the nice 3D geometry in the top panels down below. Good, okay. So we've got this nice system, and the plan is to inject domain walls into the system and study the pinning and the depinning. But it's probably a good idea to have a think about the domain wall textures before we do that. So with two-photon lithography, your printing element is an ellipsoid. Okay? You can actually calculate this directly using the Debye-Wolf vectorial diffraction. And so you can take this printing element, you can extrude it, so you've got a nice linear nanowire. And you can see that our nanowire's got an elliptical cross-section. And so if you combine this with line-of-sight deposition, so just permalloy in this case, that gives you a crescent-shaped cross-section. And that crescent-shaped cross-section we've actually demonstrated both via SEM and transmission X-ray microscopy. So why do we care about this? The reason we care about this is now at this kind of feature size, the radius of curvature is significant. So we're down at 40 nanometers, which means that our domain wall textures are actually going to be perturbed significantly from what we normally expect. And so we can do what you normally do in micromagnetics. You pin the edges, you randomize the center, you do 100 relaxations, and you see what domain walls come out. And I'll talk through those briefly. This is our minimum NG configuration. We've called it the transverse wall because it does have a transverse texture when you view it from the top. If you look from the cross-section, though, a transverse in-plane texture implies that you have opposing MZ on either sides of that cross-section. We have our plus or minus half edge defects as expected. And if you have a look at the peak of the crescent-shaped cross-section, you can see a little bit of spin canting, which is probably due to the effective DMI interaction. If we now have a look at the next highest energy state, things become perhaps a bit more exciting. I'd never seen a domain wall like this, so it's an anti-vortex domain wall. And so here what we have is, well, if we go back to our cross-section, if you look at our cross-section, I said for the transverse wall, you've got opposing MZ components in those two side arms. Here, MZ is the same sign. And if you couple that with the traditional boundary conditions for a domain wall, what you have is a formation of an anti-vortex, which seems to stabilize exactly at the apex of curvature. So again, anti-vortex -1, two edge defects of plus a half. And we think this really is probably only stable in a 3D geometry like this. And that's really because having MZ aligned like this would only really be magnetostatically favorable when you bring them spatially apart. And so we think this is something which is going to be quite specific to three-dimensional geometries. Okay, and then finally, so we've got a vortex wall. It looks quite different to what you actually have in a conventional planar system. The core actually sits off the apex of curvature. I should say there's a bit more work to do here to study how that actually is impacted by the chirality and the polarity of the wall. Okay, but what we do have is a nice idea of what type of walls that we should expect. So we now move on to experiments, and of course we do scanning probe microscopy, which we really enjoyed doing in Cardiff, and our method is to take our nanowire, align it with our fast scan axis, and to start scanning. And so we'll start scanning up until the point where we are actually tracking the topography of the 3D wire. Okay? We then disable our slow scan axis. And so what that means then is we're actually just constantly tracking over our three-dimensional nanowire. And as we actually do this, we're exposing we're exposing the magnetic nanowire to the stray field of the tip in combination with in-plane field sequences which we can actually apply. Okay, so hopefully a combination of these two fields will help us to actually inject domain walls into these systems. All right, so here's some experimental data where we've done that. These are MFM line scans, and so you can see at the top on the right-hand side, we actually have strong contrast over on this right edge, and we can see that as we actually scan, we'll move away now so you can see it, you can see that that contrast shifts, and it seems to shift stochastically between that right edge to the center, and then you get lots of stochastic pinning and depinning as you continue scanning. So what we can do then is we can actually take these images, we can binarize them, we can fit Gaussians to obtain the domain walls, and we can basically build histograms to actually say something about the energy landscape. And we can actually do that for each of the 3 nanowires that I just talked about, 1 to 5 microns, and we can also do that as a function of applied magnetic field. And so when we do that, we see distinct behavior for our 3 nanowire types, if you like. So for our L equals 5 micron wire, we see kind of distinct bands of pinning in negative field. In positive field, we just see this kind of stochastic pinning and depinning. For the L equals 1 micron wire, we see lots of stochastic pinning and depinning. Okay, so we've got this kind of these histograms, and we have AFM topography. So how are we going to try to understand the results? Well, most people would probably run to micromagnetics, but this is a bit trickier because we have things like thickness gradients, and yeah, with thickness gradients, we've got variations in roughness and so on. And so you can actually instead use a very simple model. So Olivier Frouchart did something similar in cylindrical wires. Take a Becker-Kondowski model, combine it with the model from Bruno, which is just the energy landscape due to roughness, just a magnetostatic contribution. You can combine those. That gives you a Becker-Kondowski depinning field. You can actually then compare that to the total field experienced at every point on your wire. So that includes the field from the tip and the applied field projected along the tangent of the wire. And if you do that, what we find is some agreement. So here's our Becker-Kondowski depinning field down here. We can see these regions here of high depinning field. This is high compared to what we think the actual field is that's experienced along the tangent of the wire. So we expect to see bands of pinning, which is what we see at least in negative field. For the L equals 2 wire, we've actually got on average a BK field, which is more or less very similar to what we actually calculate for the actual field, the total field actually experienced along the tangent of the wire every point. So we expect to see lots of stochastic pinning and depinning. So overall, it's a very simple model. So we capture some elements of the experimental data, but we need probably quite sophisticated micromagnetics to actually understand this further. So moving forward, MFM can get us to a certain point, but we want to go to the synchrotron, so we can now make different types of 3D ASI structures over TEM apertures. So this is a suspended 3D artificial spin ice. There's no membrane there. It's suspended. It's stable in a beam. And you can actually do transmission X-ray microscopy, for example. You can say something about the cross-sectional curvature of the wire. You can try some XMCD measurements also. So far, the contrast has been relatively weak. Probably I've hit time now, so I think I'll just put my conclusions up and say thank you.
Thank you very much, Sam, for interesting talk. I think we can take 1 or 2 questions. So, any question? Okay.
Hi, Sam. Thank you very much for the really nice talk. I had a couple of questions, if that's okay. The first one was about your X-ray imaging. So I was wondering how robust the resist is to the. Did you see any damage, basically? And secondly, I was wondering if you had tried pyrolysis with your new like resist. So if this also works with this 400, with this lower wavelength exposure. Yeah.
So when we put it into the beam, we see deformation for the first kind of like 20 seconds, but then it stabilizes. And then it's stable for the duration of the beam time. So to be honest, we were quite surprised. So that's nice. The new resist is just an acrylate-based resist, so you can use pyrolysis as you normally would do. And so this is something we're trying now. So this, in principle, allows us to realize sub-50 nanometer feature size, right? So we can combine the 70 nanometer direct write with a bit of pyrolysis to reach, we reckon, 20 to 30 nanometer nanowires. So, yeah.
Sam, thank you very much for the nice presentation. Regarding the resolution, is the complexity of your 3D systems playing a role? Meaning you have proved it for isolated structures. When you start to have the lattices, do you see any degradation or any small decrease in the resolution, or the feature sizes, you expect them to be comparable when you have complex lattices and so?
Yeah, I mean, you can just plug it into your diffraction equation. So in essence, you can make separate wires down to a resolution of around 100 nanometers with the new 405 laser. And so long as your spatial separation between the wires is more than 100 nanometers, you can resolve them.
Any other comment?
Thank you very much for the great presentation. My question is about maybe a bit strange, but how complicated materials would you be able to do, for example, with two-photon lithography? So, for example, we are interested in yttrium iron garnet, and Georg Schmidt in Halle has shown that he can do micron size, let's say, freestanding bridges. Is there a way to bring this to the dimension below micron or 100 nanometers?
Yeah, okay. So you can certainly, I think Amalia had a slide up that showed you can use TPL with a number of different deposition techniques. So you can use sputtering, you can use evaporation, you can make pores and do electrodeposition. Any kind of complex CVD type process where you have a high temperature is going to degrade the resist. And that is one of the problems. You could, in principle, what you can do is you could make an inverse structure. You could electrodeposit, so your structure is made of metal, and then you could use that inverse structure with conventional kind of YIG processes, but not directly.
Okay, let's join me in thanking Sam again.